Hello, welcome to part 2 of our exciting two-dimensional Coulomb's law problem. The video that I just had up was the same problem here, but we had done the total net force on the -6 nanocoulomb. Now I want to do the net force on the -8. And if you've tried it yourself already, here is my answer. So this is what I got. See if you got the same thing. If you did, you probably don't need to watch the video. You're probably ready. If you didn't, let's find out where the mistake was. So how are we going to do this? Same thing as last time. We need to figure out what the forces are on this charge and then add them up as vectors. So I am this +8. So now I'm a positive particle. I'm a positively charged particle. What do I feel from this negative over here? Well, negative and positive attraction, so I feel pulled in this direction. What do I feel from this negative? Negative, positive, attraction again, I feel pulled down in that way. So the 6 is pulling me down that way, the 4 is pulling me to the left, and let's figure out how big those are. We're going to use Coulomb's law. So the force of the 4 on the 8 is going to be 9 times 10 to the 9. That's our K constant. And now the two charges, 4 nanocoulombs times 8 nanocoulombs over the distance between them, 4 and 8, that's the 6 centimeters. Convert to meters, don't forget to square it. So force of 4 on 8 is, when you do that math, well, that worked out really easy, didn't it? Huh, that's interesting. It came out to be exactly 8 times 10 to the -5 newtons. And remember, this only gives us the size, the magnitude. We have to look at our picture to figure out the direction. So this is the force of the 4 on the 8. It's pulling me straight to the left. Now we can do the force of the 6 on the 8. And if we do this formula, it's going to be 9 times 10 to the 9, K times Q1, 6 times 10 to the -9, Q2, 8 times 10 to the -9 over the distance between them. And now that's this distance, which we have from the previous problem. That was the 9.22 centimeters. Convert to meters and square it. So the 6 on the 8, when you do this math, you get 5.08 times 10 to the -5 newtons. That number sounds familiar. Well, it should. Because last problem, we calculated the force of the 8 pulling on the 6, the 8 pulling on the 6. Now we're calculating the force of the 6 pulling on the 8. It's the same thing. 6 on 8, 8 on 6, this is Newton's third law. Has to be equal and opposite. So this is the exact same number we had from the previous problem. The direction is going to be opposite. Previously we had it going up and to the right. Now we know it's going down and to the left, and from the horizontal it's still 49 degrees. Alright, so you can save yourself a little bit of work if you recognize what's going to be the same if you're dealing with two questions in the same setup, I guess. Alright, got it. Now we have our forces. We need to convert them into components, figure out their x and y components. All right, we have the force of the 4 and the force of the 6. This is the easy one. It's all in the x direction. There's no y component at all. The whole thing is, I'm just going to go 8. Again, I'm going to ignore that times 10 to the -5 for now. It's to the left, negative. So in the x direction, for this force, it's all in the negative x direction. The 6 on the 8. Now we have something like this, and as I did before, I have to figure out what its components are. 5.08, 49 degrees. I already did this triangle. I just had it going this way. It doesn't matter if we're drawing it this way or this way. The size of those two sides is going to be exactly the same. Which means that I'm going to have, in the x direction, 3.33, and in the y direction, 3.83. 3.33 and 3.83. That is exactly the same triangle, it's just down left instead of upright. Which means these two should be exactly the same as the 8 on the 6 with the opposite signs. My x direction here is a negative 3.33, my y direction is a negative 3.83. If you go back and look at your notes from the previous problem, you should see that both of these were positive last time. It's just a good way to double check that you have your numbers right. You can compare against something else. We have all our components. Let's add up the x and the y. That's the easy one. Negative 3.83 times 10 to the minus 5 newtons in the y direction. In the x direction, 8, 9, 10, 11, minus 11.33 times 10 to the minus 5. All right, so we have an x component that's to the left and big, a y component that's down and medium-sized. Does that make sense? Well, yep. We've got a lot going to the left and a little bit down. Here is our components for the net force, the total force. Let's figure out what the actual values are for the force as a vector. I have left and down. Okay, so I have 11.33 going to the left in the x direction, 3.83 going down in the y direction. There are my components to the net force, and I want this vector. That is the net force I'm looking for. If I do the Pythagorean theorem here, 11 and 3.8, then it has to be bigger than both of those. And what I get for the size is 12.0 times 10 to the minus 5, which I'm going to convert to 1.2 times 10 to the minus 4. So that's the size of it. Vectors have size and direction. My direction, going to do the inverse tangent of opposite over adjacent. Opposite, 3.83 over adjacent, 11.33. And just looking at it, I'd expect a reasonably small number. What do we get? 19 degrees? Yep. So my angle, 19 degrees. All right. Now remember, that 19 degrees doesn't describe it well enough. That 19 degrees could be anywhere. So the best way to give it is either at 19 degrees south of west, or if you do the 0, 90, 180, 270, if you do the circle, then it would be 180 to here plus 19. It would be positive 199 degrees. And now if you look at these two, they have nothing in common. The net force on this is pretty small, 3.4 times 10 to the minus 5, and it pointed that way. But the net force on the h, which we just solved for, is big, 10 times bigger, almost, and it's pointing down and to the left. So you can't assume that just because you've solved for the total force on one of these, that the total force on another one is going to be anything like it, because it's got different forces acting on it. But we can kind of double check and make sure, well, does this make sense? The same force. We had 8 on 6 previously. Now we have 6 on 8. Those need to be the same force, opposite directions. So these two should be the same as before, but the previous ones better be plus and plus. Same process. So we've got the process of figuring out what the forces are, breaking them up into vectors, components, adding the components, putting those components back into a vector. And then that gives us our final answer. Is it reasonable? Well, again, it's hard to tell, is 1.2 reasonable? Is 12 times 10 to the minus 5 a reasonable size? Well, we had an 8 and a 5, so I guess 12 is in the same ballpark. And then does down and to the left make sense? Absolutely. We have 2 going to the left and 1 going down, so that final vector has to be going down and to the left. So that's about what we've got. We can check that we've answered the question. Yes. What is the net force on the plus 8? I guess it makes sense. We have units on it. We've answered the question, and it all makes sense. So that one was pretty fast, wasn't it? We can take advantage of what we did previously because we know a whole bunch about this from the way we did the problem before. So that's what we've got. The plus 8, the force on the plus 8 is right here. And then the previous one, the net force on the minus 6, right there. Okay, good job.